Okay, so finally let's start talking about finite automata and specifically deterministic finite automata. So what is DFAs? So you can think about it as the simplest, interesting model of computations. So we have a program. The program has a state, but the state is, very bounded. You need only a few bits to describe the states. And these kind of DFAs are in fact widely used because they are so simple. They are very easy to, encode in, build the physical circuit that implements them. So you see the kind of logic in a lot of things like vending machine, elevators, etc., etc. But in fact, they are also used in a lot of other places because the notion of state is so fundamental that, you use it even in large projects to kind of model the state of the system. The real state might be much more subtle because there are a lot of other arguments and variables that are being used, but you can have a state diagram of your system. By the way, those state systems nowadays, you can use hierarchies and stuff like that, and people use them to model the system. And then what happened is that, you use the DFA as a way to describe the behavior of the system in high level. So in fact, while directly being used, the use is kind of narrow. In fact, it's so widely used indirectly everywhere that it's really a very useful way to think about things. Okay, so let's start maybe from one of the simplest examples. We want a program that reads a string and tells us whether or not the string has odd length. Okay, so writing this in pseudocode is very easy, right? You just init a counter n, and you read every character as long as the input is not empty. And every time you read a character, you increase the counter by 1. Right? And then when the input is done, then we just check whether the counter is even or odd, and we output, yes or no accordingly. Right? If it's odd, then we say yeah, and we output yes, otherwise we output no. Okay, so this is the basic idea. Now, the important thing to observe here is that we don't really need a counter, right? What we really need is just a bit that tells us the number of characters we had seen so far is even or odd. So in the beginning, of course, the number of bits we saw is 0. And now, every time you read an input character, you just flip the state of the bit, right? The way to think about it is really that we still maintain the counter, but we care only about the first bit of the counter because that's the only bit we need for the output. And then in a similar way, we just output the bit in the end of the run of the program. And the important thing here is that here we really literally used one bit to remember what the state is so far, whether the number of characters we read so far is even or odd, right? This is just the parity bit. Okay, so here's the way to think about DFAs. The input comes on a tape. Tape nowadays is a weird way to think about things, but in the past that was a natural way to think about it. So we have a tape, and the input is written on the tape. Now, we start reading the character written on the tape. The tape has cells. Every cell contains a single character, and we start reading them. And what the DFA does, it's a one-way tape. So it starts reading the tape, and every time it reads a character, it does some operation. It updates its internal state. Right? Essentially, it reads the character, does something to update its state. Then it moves to the right, read the next character, and so on, until it reads the last character, right? And at that point, it stops. And the important thing, of course, is that, the assumption is that it has this state machine has an initial state before it read all the input, and then it's, as every time it handles a character, it moves from the current state to some other state. Some of the states are marked as accepted. So if in the end of the reading all the character inputs, it's in an accepting state, a state that is marked as this is an accepting state, then the machine would in the end turn on the light, right? It would be red. It's a red light. If on the other hand, in the end of reading the input, the DFA, this control mechanism is in a state that is not accepting, then it rejects, and then the light is off. Okay. Now, it's useful, in fact, to think about the DFA as not knowing when the input ends, right? So it's read a character, update its states. If the state is accepting, it turns on the light. If it's not accepting it, it turns it off or keeps it off, and so on until it's done with the input, right? So it goes from left to right. The light turn on and off as it get into accepting states, and then we care about what the state of the light is in the end of the input, right? But the DFA inherently in advance doesn't know how many input characters there are, and in fact it doesn't know when it's in the end of the input. We know it because we feed it the input, and then when we are stopping to feed it, we can just ask, is this current state accepting or not? And as such decide whether the input is accepting or not. But the DFA, in some sense, is oblivious and doesn't know. Okay, so draw me a ship, draw me a DFA, I meant. So if you don't know what the reference is, this is a reference to a book called The Little Prince, which I highly recommend that you read if you have not read it during your childhood. It's a very nice book. So let's try to draw a DFA for the counting of the whether the input string is odd length or even length, right? So we are going to have two states, right? The number of characters we read so far is even so far, right? And odd so far, right? And by odd so far, I mean this is really number of characters read so far is even, okay? And the same thing for the other state, right? Now, initially we read no characters, so the length of the string is 0. So we start in the even state, right? So we designate it by having an arrow, right? So how do we draw a DFA? We draw the states. Every state is just, going to be a circle or something that looks like a circle. Usually, we write inside the circle a name for the state that kind of either the description, but usually just some unique identifier. And then the state that is the starting state where the DFA starts from in the beginning, it has an arrow that comes into it from nowhere. Okay. And now what we have to do is to say what happens, right? So let's assume, for example, that now we are walking over the most boring alphabet, which is just 0, right? So sigma is just the character 0. So if we get the character 0, and we are in the even state, then we have to go to the odd state, right? So we draw an arrow from the even state to the odd state, and we put 0 on it, which says we got the character 0 in the input cell. As such, we have to move to the odd state. Okay, and similarly, if we're in the odd state and we get a 0, we go back to the even state. So this is the automata, except that I have to tell you what is the accepting state, and this we designate by drawing the two circles around around the state, except that here I made a mistake because here we wanted the odd length string. So the odd length string would be this state, right? So we draw a circle around it, right? So this says the odd state is the accepting state. There might be many, so a DFA might have a large number of states. There is only one start state. And the DFA accepts if it ends up in the end of the input in any of the accepting states. And similarly, it rejects if it's in any of the rejecting states. Okay, so this is how it looks like. And the nice thing about DFAs is that drawing the state diagram, in fact, is natural and relatively easy, which makes a lot of this thinking about this stuff easier than one might expect. Okay, this is it for now.